All right, integrated superstars, thanks for joining us for the 2.3. Oh my gosh, 2.3, you made it this far? Check you out. You're here for the 2.3 introduction to the Ready, Set, Go. I hope you're having an awesome day. If you're watching this in a public space, that's cool. If you're watching this on an airplane, I hope you have your airplane mode turned on and you have your seatbelt fully fastened. If you're watching this in your home, then that's cool. I hope that you don't have any distractions nearby. So let's dive into it. 2.3. First, we're going to be comparing rates of change in both linear and exponential situations. Just a quick refresher on these two. Linear means that this is a straight line. Occasionally, we see these written out as y equals mx plus b. Previously in Module 1, we might have thought of these as arithmetic sequences because it was just adding the same number over and over. Shane McGinty said that amateurs add, and add starts with A, whereas if it's exponential, it's going to be going pretty crazy pretty quickly. And we could have those equations look like this. We could have A and then B and then X. And this is similar to when we dealt with a geometric sequence. And we say that real G's multiply their money. So that's why that's going so much quicker. All right, so with this first one, identifying whether situation A or B has a greater rate of change, we're given a table, we're given a graph, we're comparing the two. Again, we're just comparing 1A and 1B. So I know that with this graph, how can I get the slope of this? Well, I could do rise and run. I could know that my run is +1. I know that my rise is counted 1, 2, 3, 4, 5, 6. It's +6. I know that our rate of change is 6/1, which is just +6. For the table, we can get some common differences here. So the change from -48 to -43, that's adding 5. From here to here, it's doing the same thing. From here to here, it's doing the same thing. Just making sure that's consistent with our x values. That's just adding 1 over and over. So our rate of change, remember, we can call this our change in, previously it was change in f of n over a change in n. And here we'll do change in y over the change in x, which is eventually leaving us with 5/1, which is just 5. So what do you think? Which is greater, 5 or 6? Hopefully you're saying that B is the steeper slope because 6 is greater than 5. Or rather, the absolute value of 6 is greater than 5, but B in this case is the best. 1 and B are geometric or exponential, as we now say. They look very similar. They look as if they hit the same y-intercept of 1, so that's interesting. But visually, what do you think? Which one looks as if it's rising quicker? Hopefully you're saying B, because from here to here, that's quite a leap, whereas over here, it takes a little bit more time to get there. Graph B does this in one move to go to this point, which is 1, 6. Whereas over here, it takes them like 2.3 x values to go to 6. We got some word problems here. I'll guide you through some of these. We have Lee with $25 withheld each week from his salary to pay for his subway pass. Okay, so we're holding on to $25. Jose owes his brother $50. He has promised to pay half of what the debt owes each week until the debt is paid. Okay, interesting. So this is taking $25 every week. So every week we're just taking 25. Whereas over here, Jose owes his brother $50. He has promised to pay half of what he owes each week until the debt is paid off. So think of this as starting at 50, but then what's week 2 going to look like? It's just 25, right? And then what's half of 25 going to be for week 2? Hopefully you're saying $12.50. So let's compare. Lee has $25 withheld each week from his salary to pay for his subway pass. I think that B's in this case going to work the best because it's not arithmetic, it's geometric. So it's going to be moving a little bit quicker. Or well, this is an interesting one because from here to here, this is changing 25, whereas this is consistently changing 25. So I would actually say that this is going to be better. So disregard what I said there. I think A is going to work better because Lee is holding 25 every week, whereas Jose is paying 25 at first, but then it's $12.50, and then it's going to be $6.25, and then it's going to go down from there. Hope that helps. Let's keep going. We have, we'll do 5. So we have our exponential equation, 2 to the 5x power on the left. In the children's book, The Magic Pot, every time you put one object into a pot, 2 of the same objects pop out. Imagine that you have 5 magic pots. Okay, so this is saying that we start with 5. So you have 5. And maybe drawing this out. So, okay, every time you put one object into the pot, so maybe let's draw a pot. Every time one goes in, 2 of the same object come out. And we have 5 versions of these. So we have 5 versions of this pot where we get several versions of 2 depending on every time. So we could think of this as 5 versions of this pot. So 5 versions of this pot right here. And they produce 2 every time we put one in. So what do you think? What moves quicker, multiplying by 2 by 2 by 2 or by 5 by 5 by 5? Hopefully you're saying this one. Your common ratio is stronger here. If you're not convinced, you could try this out. You could check. I mean, you could try to graph these out too, but really putting together the equation here is a good place to start. This takes us to the set where we're recognizing linear and exponential functions. They have more words here, but that's okay, nothing we can't handle. Population of a town is decreasing at a rate of 1.5% per year. Okay, so we have our population. And if it's decreasing 1.5 every year, it's really multiplying with 98.5 every year. Sorry, 0.985. Because again, we're dealing with a decimal here. So since we're decreasing, we're really multiplying it by 0.985. Sorry. So we're just determining if it's linear, exponential, or neither. This is going to be exponential because every year we keep tacking on another 0.985, and that's consistent every year. Okay. If it's linear, we can take it to y equals mx plus b form, and we only have a single x. We don't have x squared or anything like that. So if you wanted to rearrange this, you could. You could say it's 4y equals negative 3x minus 3. If you divide everything by 4, you'd say that y equals negative 3/4 x minus 3/4, and boom, now it's linear. And it's cool with these. I mean, just being able to write down what it is fine, but being able to show why, I think, is even stronger. Okay. So That takes us to our visual here. This looks as if it's going down and then drastically dropping quicker and quicker. I'd say that this is exponential. I hope that helps for those. Being able to draw out the equation, I think, is a big part there. This takes us to the go, getting geometric means, nothing we can't handle. Lots of tables here. I'll kind of hop through everyone here. So this is asking us to find the missing terms in the sequence. Since it's geometric, again, real G's multiply, and sometimes they divide to get the next term in their sequence. So how we do this, we can take the final Y value, which is 162, and we're thinking out that we have to jump from 2 to 162 with, count them, 1, 2, 3, 4 moves. So that's saying that 2 has to multiply with something 4 times to get to 162. So we can find out our geometric mean if we divide by 2. Remember, this 2 is from right here. So 162 over 2 should get us 81. So much fun. We're then thinking out, based off of these, count them, 1, 2, 3, off of these 4 steps, moving along 4 terms. There's some term that when multiplied by 4 gets us 81. And in this case, it should be 3. Positive 3 in that case. So we can take our previous term, multiply it by 3, and we'll do that here. So 2 times 3 gets us 6. 6 times 3 gets us 18. 18 times 3 gets us how much? What do you think? Hopefully you're saying 54. And lo and behold, 54 times 3 gets you 162. So we're in good shape. If you're not convinced, check a calculator, but this works, trust me. We can then take this further to here. So we're now jumping from 10 to 0.1625. A little challenging there, but the same kind of idea as we saw up here. So I'm taking the final value. I know that if I divide it with the 10, this number is going to be pretty ugly, but it's nothing I can't handle. If you use a calculator for this, we got 0.625 dividing with 10, which is saying that there's some number that when multiplied by itself 4 times gets us, what was the number again? 0.0625. And you could just guess what fraction it is, but I think one better approach is to just find what the 4th root is, which seems like some more complex math, but it makes sense because if we take the 4th root of x to the 4th, and we take the 4th root of 0.0625, that'll leave us with what our common ratio is. So in this case, what I'm going to do, follow along with me. This is an important part. So I'm taking 0.0625 on my computer. I have the scientific calculator. All right. And then I'm hitting this Y, computing the nth root of the displayed value, where n is the next value entered. Okay. So I'm clicking this. I'm clicking 4 because, again, it's our 4th root. And I'm hitting equals. Okay. So 0.5. So that means that every time this moves forward, the previous term is multiplying by 0.5. And if you're not convinced, let's try this out here. So 5 times 0.5 would just give us 5. 5 times 0.5 would be 2.5. 5 times 0.5 gets us 1.25. And maybe we'll use the calculator on this one, okay? So with this final bit, just to confirm, 0.5 times 1.25 should get us this final value here. And that's true. So I know I'm good. Boom. You got some more slope problems here. They're just throwing in more. That's fine. Okay. 11 to 4 would involve subtracting 6. Well, hold on. Let's look at this a little bit more closely. So this would deduct 7, and then it deducts 3.5, and then it deducts a little bit more. Okay. So we actually might want to take our time on this one. So we know that these are getting a little bit more complex because it's no longer just adding the same number over and over and over. I mean, maybe for this one it is, but you know, maybe, all right, well, yeah, we'll kind of go for this one. Okay, so this one's not too bad. 13 to 23, that's just adding 10. 3 to 8, that's just adding 5, and hopefully it's consistent here, where from 23 to 43, this is just adding 20. And from 8 to 18, this is just adding 10. And so hopefully all of these numbers, when we get our rate of change map out, because we should be saying that 10 over 5 equals this 20 over this 10, which equals this 10 over this 5. And if we simplify all of this, this is just giving us 2. So that's actually our rate of change. So we found that, again, just being consistent with how we work this through. And I actually now see what I was doing over here. Okay, so we're still going to do the same thing here, but 11 to 4 is going to be deducting 7. Here to here, it's going to be adding 2. And so just based off of those situations, we should be saying that our slope is -7 over 2. If you're not convinced, you can keep going to the other numbers, which I think is a plus. So this was -3.5, and this was just adding 1. So this is -3.5 over 1. Eventually, if you do this final one, it should just say that your slope's -3.5. Staying alive. So if this was graphed out, how would it look? This one right here. Hopefully you're saying it would go down to the right. This one would go up and to the right. We're getting the slopes down here. We haven't seen slope formula yet, but I'll walk you through this. So we can label this as our first point, x1, y1. This is x2, y2. We use this equation, y2 minus y1 over x2 minus x1. If you map these out, you could use rise and run, and this is kind of the same thing that I'm going to do, but the difference between 29 and 5 is just 24. The difference from 8 to 2 is just 6. If we simplify 24 over 6, it's just +4. Does that help? Does that make sense? If you're stuck, let me know. Thanks for watching.